Welcome back, everybody, to the second part of today's lecture. We're going to start with a question on MapReduce that I think a student in the lecture hall has. Maybe we can pass the microphone, or how do you want to handle it then?
Yeah, I just wanted to ask, like, we had the document IDs that the mappers used, and how do we get them to agree on all them? Do we just like set them beforehand, before we start this MapReduce?
There are several ways to go about it. What you can do, for example, what's typically done when you have large-scale computations and you want to generate IDs, you can generate an ID out of the ID of the machine that is processing the data, plus an additional ID that is unique within the machine. So this is how it's typically done. So you could assign a document ID in that way, based on the some footprint of the machine plus an increasing integer within the machine. This is the first way. A second way is what is called, especially in technologies like Spark, a monotonously increasing sequence of integers. What that means is that it's not necessarily a contiguous sequence that is going to go from 1 to a billion exactly with 1 increments. But basically, it's a process that guarantees that all the IDs that are produced within the system will be in increasing order, but potentially with gaps. And the way it's typically done is that each machine gets assigned a very, very large number, like, for example, 1 billion, and then adds to its number smaller numbers. So you basically maybe go from 1 to 10,000 on the first machine, then you go from 1 billion to 1 billion and 20,000 on the second machine. Then on the third machine, you go from 2 billion to 2 billion and 15,000 and so on, which as a whole gives you plenty of integers that are guaranteed to be in a monotonous sequence, but not necessarily contiguous. This is the second way that you can do that sort of things. And the third way is that if you're indexing the web, then the URL of the page can be used as the ID, because this can be considered an identifier of the document, as you know, the one you type in your browser. Did I answer your question?
Yes, thank you very much.
Yeah. All right, very good. These are all advanced things, right? So it's when you start doing distributed data processing with MapReduce or Spark, then they typically have this kind of feature. Snowflake probably has something like that. It's even something that is available in the SQL language. Many SQL engines, local or distributed, provide you with a way of generating IDs like that in parallel. All right, are there any other questions? Anybody else? No questions. So I hope it means that you understood everything that I'm telling you, right? I'll check at the end, but I do hope that this is the reason. And otherwise, you can always interrupt. Let's continue then. What I was promising to you is what happens if we have indexed an entire collection and then somebody arrives and says, okay, I want to add 1 book to the collection. What do you do? So imagine, so we have constructed our index like this, and then this happens. What do you do? Well, you could say, okay, we just need to do it all over again. We just need to reconstruct the entire thing out of this new collection, and now we have a new index, right? So, but maybe that sounds a bit exaggerated, because that literally means that as soon as somebody edits a web page somewhere, you need to retrigger the entire index of the entire web, right? That doesn't seem like something that can scale. So obviously there are other techniques that are able to do it in a more dynamic and incremental fashion, right? Okay, so you see, yeah, this is here, literally, this is really reconstruct. Like every time I redo the whole thing from scratch with everything, right? Okay, there are several problems. First, it takes a lot of time to construct. Maybe it can take, typically, if you're a search engine, it can take up to 2 days for doing that sort of things, right? The time it takes is absolutely enormous. 2 days is even just partial. If you really want to reindex the entire web, I don't know, maybe it's going to take you 1 month. These things evolve so fast that it's hard to tell nowadays how much time it would take, but a lot of time. It's not something that you just do it just like that in 1 second, you reindex everything. So that causes result stainless because every time you need to wait to see the actual reconstructed index. And the other aspect is that while you are reconstructing, maybe you will be completely unavailable or slower during index construction because all your machines that are used for querying, they are all constructing the index. That's taking a lot of CPU, right? Unless you divide your machines into 2 machines, right? Those that work, it's like a technique used in computer graphics, right? The double buffering, that you have half of your machines serving and the other one indexing, and then you just swap the roles every month, right? But anyway, this is not good. This is not good at all. So we can do something else. Another way of doing that is a so-called auxiliary index. What that means is this here is the entire index that we've spent a month building, right? It's all there. And what I do with the new, sorry, I think that's called the Frosch im Hals, I think in Deutsch. Anyway, so now with the new documents that have arrived, I'm building an index, but just with them. It's going to be smaller. This one is enormous. This one is smaller. Maybe it even fits in memory because these are not so many that recently arrived. And the other is on disk, the entire internet. Okay, so what do I do then? Well, if somebody queries for a word, for example, computer, then I will just look up at both places. I will look up on disk on my very, very large index for the old documents and find all of these postings. And I will also look up in my auxiliary index in memory at the same time. And then I just union these two right there every time. So I just query both. That's one way of doing it. And at some point, of course, this index is going to grow, right? As more documents arrive. And then, of course, at some point, it occupies the entire memory. What do? I just merge it back to the actual index on disk. And now this is my new old index where I merge the auxiliary index. And I do this periodically. Every time it fills up the entire memory, I just merge it back to disk like that, right? And I'm back to having an empty auxiliary index and I just continue, all right? The advantage of doing that is that if you have increasing document IDs, these are just simple appends, right? Every time, you just add the new document IDs in there. But of course, it only works if you create documents. If you modify documents, then that doesn't work anymore. But if you're a library and you order books, then you never update a book, right? You can have a second edition of a book, but you will not actually erase or replace the content of a book. So it kind of makes sense. All right, and appending is something that's quite efficient. All right. Moreover, if you do it that way with appending, every time you have one seek on the disk, because then it's all sequential, right? So this can also be handled in an efficient way with one seek for every file. So maybe you have one file for every term. We'll see also that we can have a file with several terms if we want to diminish the number of seeks, right? So you know seeks are costly every time you seek something on a drive. Anyway, so we have this technique with the auxiliary index. We've merged it all on disk. What if a document gets deleted? How can I deal with it? Because all I can do is add things, right? I can add new things in memory, but I cannot remove things from disk, right? It doesn't work. It's not so easy. It would be inefficient. So what if a document gets deleted? Well, this can be done with a bitmap like this. So it's just an array in memory with 1 bit for every document. And I can mark a document as deleted. That's also called an invalidation bit vector. So it's zeros and ones. It's a 1 if the document is still there, and I flip it to a 0 if it gets deleted. And this is in memory. This is 1 bit per document, right? That's not so much space, right? Even if you have a billion documents, we are talking about 1 billion bits. So it's an 1/8 of a gigabyte. So that's roughly 128 megabytes, right? So it's reasonable. So that's called an invalidation bit vector. What happens is that then if you read from the index, you're checking for every one of the document IDs that you find here. You just check it in the invalidation bit vector. And if it's marked as deleted, you just block it. Then you don't return it, even though it would have been on disk. But here you just post-process by filtering it out. All right, so this is how it works. And this is actually how deletes are very often handled modern databases that have storage that they can only happen, a deletion is only a marking for deletion that gets added, but it's not immediately getting deleted. Maybe you can delete it the next time you merge it back to disk and you rewrite the entire index. That's the next opportunity for deletion. All right, so as you can imagine, if you have 500 million terms in there, one file for every posting list is not practicable. So what you can do in order to reduce the number of files, because 1 million files on your laptop doesn't work, you can group several terms in the same file. So that's a level of granularity here. Here it's one file for every term. Here it's one file for everything, right? And then you can slide in the middle. So if you're here, it's more efficient when you write, you have a finer level of granularity. And here you diminish the number of files and you just need to find your sweet spot. Yeah. Okay, so now, what's the complexity of that, of this protocol of auxiliary index that we just merge back to disk regularly? Well, imagine that we have the size of memory can have n postings, right? And I have t in total that keep incoming dynamically. So if every auxiliary index in memory has n posting, how many times am I going to merge? Well, t divided by n, right? Because the number of merges is just the division. T in total, n per packet, so the number of packets is t over n. Okay, the complexity for a merge is linear, and that's on the side. So here we have n for the first time, it's just writing it, then 2n when you merge it the second time, and at the end, it's the entire data that is merged. T. So it's basically n plus 2n plus all the way to t over n times n. T. So you know the formula, right? For 1 plus 2 plus blah, 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 it's nn plus 1 over 2. And if you actually apply this, then you get a complexity analysis that gives you something quadratic in that. Quadratic isn't that great, right? It's even sorting is not quadratic, right? So that's not really that great to have a solution that is quadratic in the number of tokens. Can we do better than that? And yes, the answer is absolutely yes. We can do better than t squared over n. All right, so let's do better then, if we can do better. So how does that work? Well, this is a magic trick that is absolutely lovely. And it's something that is very widespread also in large databases. The technical word for this is called log structured merge tree or LSM tree. But the way it works is best explained with an animation of what's going to happen. This is a logarithmic way of creating the intermediate indices. So here's what happens. We still have this idea that we have these incoming tokens that accumulate into memory in the auxiliary index. Of course, we start with nothing on the disk. So we have accumulated something that fills the entire memory, and we said n postings, n postings. N is my number of postings there. So I have in total n postings in there. So it fills the entire memory. What do? I just copy it over to disk. I call it I0 because that's level 0. Then I again accumulate. So this is the long-term index. This is the auxiliary index. And now I fill the memory again. So what I do is that now I merge these two together, creating 2n postings. So it's double. And now I put it back on disk. Of course, here I did it in memory, but actually you can do it entirely on disk, right? You don't need to materialize that in memory. But anyway, now I have something that I call I1, but it's double as big as twice as big as the first one. Now I continue accumulating, then I put it on disk. Now I have two, that's new. That's new. Now I have two indices on disk. I have one that is like the double version and here the simple version. Plus I continue accumulating stuff in memory. So now I have 3 places to look at whenever I query, right? So here, here, and here. Next, what I do is that I'm full again with n postings. So I merge these two, but then I also need to merge that, right? So I create now 4 n postings and then put it back in memory. Now that's level 2. Then I continue, I fill memory and I put it in there. Now I have a quadruple size index plus a normal size index, and I continue accumulating. So 3 places again to look. Then here it's full, I merge it back. Now I have 2 indices on memory, the double and the quadruple size, and so on, right? I continue to merge. Now, I know you're smart and you probably recognize counting in base 2 with what was happening in there, right? Look at it again. So this is this is 1, you just need to mirror left to right, right? So imagine the units are here, and then it's just in the opposite order of writing numbers. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 4 plus 2, yes, and this is 7, right? And then comes 8 when you merge and merge and merge, and you cascade into then level 2, right? That's how you get the actual 8. Okay, so I hope you understand the trick now. It's really this idea that you double and double and double and double. And actually, as somebody noticed in another lecture, this is exactly like this 2048 game. Who knows the 2048 game? I'm pretty sure some of you played that game. It was very viral at some point on the internet. Does anybody have anybody heard of that game, 2048? You have these numbers that arrive, and every time you touch twice the same number, it creates a bigger number. Exactly, so you know it. So think of it as the 2048 game, right? You just touch and double every time you merge two indices. Well, this is absolutely great because it solves our problem. Because if you look at the complexity of that, now, of course, we don't have just one index. Now we have log of t over n, right? That's just the size of a number in base 2. That's log of n, right? It's the logarithm. So now we have this number of index, and the construction time is t log of t over n. The query time is the logarithm of t over n. So we basically now have something much, much better than quadratic. We have t log t, basically, like 13. So you see, it's a compromise that we make between construction time and querying time, because here the querying time, it used to be almost constant time, right? O of 1. Now it's O of log t over n. Why? Because you need to look up all of these indices that you have on disk. So it's a compromise, right? We had a very good querying time. Now we improved the index construction at the cost of being slightly slower for querying, right? But this is how it works in computer science, right? There is no free lunch, so you always get something by paying in another way, right? Like time and space. Okay. In practice, though, what is done, and that might actually surprise you, but this is what's done. We very often use this index reconstruction. We actually do rebuild the entire index, but with this double buffering like setting, that you keep some of your resources with the older index that is just frozen in time. And at the same time, in the background, you create the newer version of the index. As soon as it's ready, you do a hot switch. You just move over to the new one, delete the previous one, and then build it all over again. So this is why you get this 48-hour staleness over the internet when the search engines constantly rebuild their indices. Of course, I'm oversimplifying probably because I'm pretty sure that the complexity nowadays used by the Google, Bing, Yahoo, and so on is probably more evolved than just that. But on the high level, this is pretty much how things actually work. Okay, now everything we did today was based on the standard inverted index. Set of words, no positions, because I showed you the extended versions of the index, right? These ones. For example, we have the positional indices where we add the positions of the words to answer phrase indices. No, sorry, that's this one, where we add the positions. We had the by-word indices, 3-word indices, 4-word indices, and so on. It's almost straightforward to adapt everything we've done today to these indices. It's almost the same techniques. You just slightly modify what you actually store in there, but all the techniques just apply in exactly the same way, right? So it's just easy and straightforward. All right. Now, this way of proceeding with the documents that are nicely sorted like that is good for Boolean queries. In fact, this is the Boolean query language we looked at the very beginning. But it is not made for ranking, because it probably didn't escape you that when you Google for something, you actually get ranked results, right? You get the first one, the second one, and so on. And it's rare that people go beyond maybe the second or third page, very rare. But I haven't talked about that at all. I never told you anything about ranking results so far. I just told you about the set of the resulting documents, but without any ranking. This is going to come in probably 2 or 3 weeks, where we are going to see into how we can actually rank the documents. It's beautiful. If you love linear algebra, you will love it because that uses linear algebra. Just like machine learning people love linear algebra, We also use linear algebra for ranking queries. All right. It doesn't involve any security at all, right? What we did also, because you also might, if you, for example, if you're a legal company and you have internal documents that you want to index, that's actually an important use case of information retrieval, right? For the paralegal teams, for example, that have to query past documents. So you might also want to add security in there with access control lists and who is allowed to visualize the document and so on, all right? Everything I've told you in that section, so we started last week and finished today, is chapter 4 of the book. And you should really, really read it. That gives you another angle, even though it's very close to what I explained, right? So here, I just waved my hands and explained to you on a high level, but the book will give you another angle and maybe go more in depth about some of the things that I've shown you, right? So you really, really need to read that chapter of the book. So right now we are just going chapter by chapter. At some point we'll skip chapters and not do everything because there's plenty of machine learning in there. And of course, I'm not covering machine learning, but you'll see, we will make progress throughout the book as we go. All right, this is the end of this section. Does anybody have questions about what we have done on index construction? Does that mean that everybody, so who understood what I've been telling you? Please raise your hand on Zoom or in the lecture hall.
Well, we have a question actually.
We do? All right, let's go ahead.
What's the difference between terms and postings? The T variable seems to be used for these.
Right. So this is something that in the next section we will again. I will explain more the conventions. So what we call a term is what there is in the standard inverted index on the left. It's what we have in the keys of the B tree, of the B plus tree. So if I can show, oh, did I lose my screen? No. All right. These are the terms. This is what is in there, right? So these are unique, and this is after the pre-processing, right? So it might be that here there is computer computing and so on, all grouped in there, right? So these are the terms in there. Tokens. The tokens are what you get during the processing phase when you prepare your documents. And for example, you use the spaces to tokenize your documents. A token is what there is between two spaces to oversimplify things, right? So it's one location in the original document that is a very specific location there. So it's very early in the process that we use the word token. More precisely, that would be a positional token. A positional token means it's at that very specific location in the document. So one term in there can correspond to several positional tokens, right, in the original document, because it might be at plenty of places and conjugated in different ways if it's a verb. So that's the positional token. So when we say token, we very often mean positional tokens. Now, what we have here, this is what we call postings. A posting is something in between. A posting is an occurrence of this term under any form, any conjugation, any case, and so on, plural singular, in document 1. In other words, formally, if you want to express it mathematically, it's a pair made of a term in a document. This posting here is the pair A1. This posting here is the pair D3. So you can see that a term can correspond to plenty of different postings, and the posting can correspond to plenty of tokens, because here we have the pair D3, but the term D in document 3, maybe it's there 5 times. So here we have one posting D3 that might correspond to 5 tokens in the original document, right? So this is why we say a positional token, and we say token meaning positional token, And we say postings, meaning non-positional posting in that sense, because there is no position at all. Now, we can also use the expression positional posting. So what is a positional posting? A positional posting is in this index right there, that you have this special extended index that contains the position. Here, these are positional postings. It's a triple made of a term, a document, and a position. This is a positional posting. Did I answer your question? Does it make things clearer?
It does, yes.
All right, because this is really very precise, right? It can all be expressed very formally. The only difficulty, because of course, this is the real world. In the real world, if you talk to different people in different countries or different universities, maybe some people are going to use words in a different way. So I don't guarantee you 100% that everybody is going to use the word term and the word posting and the word token in the same way. But at least for this course, I'm trying to be consistent in the way that I use this, all of this terminology to not confuse you too much. And normally it should be aligned more or less with the book. All right, any other questions?
I also see another question in chat. I'm still wondering about the entire organization of keeping track of document IDs, term IDs during dynamic index building concepts. And then he says, but I guess I should read the book first.
Yeah. So here you probably refer, because there are many techniques, right? There is not just one. So for example, for offline indexes, we looked at 3, BSBI, SPME, and MapReduce. And then there is the dynamic updates. This is kind of orthogonal. You can have something dynamic with BSBI, you can have something dynamic with SPME, you can have something dynamic with MapReduce and so on, right? So you can basically mix and match, and it's a whole combination of things. So you basically need to think these things through for every single combination that you are looking at. So the document IDs can be created. You can use, for example, one way would be a combination of the machine and the timestamp, for example, the time of the day, the date and time of the day that is guaranteed to increase. So it really depends on a case by case basis. Right. But here you're really already looking into the finer details, which is great, because that's the sort of details that you will be forced to actually figure out when you actually build a system. What I'm giving here is the general guidelines for building a system. And of course, what you need to think about, it's basically something here. I'm really connecting with the data structures and algorithms lecture on this, because the idea is what you want to do is have an order of the documents. The most obvious way to do that is to use integers, contiguous or not contiguous, as we saw. So if you use integers, you have an order. Maybe you use strings like the URLs, and then you can order the string with a specific, it's called a collation when you order strings. And then, you know, in many programming languages, there are ways to specify an order, and then you specify it in templates when you use, for example, sorted lists and so on, right? So you can specify your own sorting, your own comparison function, for example. So you see, this is, we are getting technical here, but this is pretty much how it works. And another aspect of that is, do you keep it all unsorted and just throw around your document IDs and it's not sorted, and at the very end, when you create the final inverted index, you pay for an n log n to sort it? In some of the architectures, this is how it's done. You don't care about the sorting, but you pay n log n at the end. Or you prepay, it's like a prepaid plan, where you proactively use a tree structure, a binary tree, or any structure that maintains an order, and you basically pay this n log n, but as a monthly flat rate, basically. You basically pay as you go, but then at the end, that's it. It's already sorted by definition of the data structure that you're using. So you see, there are these two ways of doing that, and both are fine. It really depends when you want to put the computations, on as you go, or as a single payment at the end with a final source. Right. Did I answer this question? All right. There are many ways of building these systems, and I'm pretty sure if you go to Google, if you go to Bing, if you go to DuckDuckGo, or any provider, I'm pretty sure you will find that they do it in different ways. They will make different engineering decisions, maybe because of the machines they have. They don't have the same number of machines. So what you need to basically learn as part of your studies is the general guidelines and all the knowledge in such a way that later, if you are put in the position of actually building the system, you are able by yourself to make all of these decisions. Right? I'm basically giving you the algorithm in order that you can make this decision. Okay, any other questions? Otherwise, we'll move on to index compression.
Yeah, I think we can move on.
All right, perfect. All right, so here I just need to, for clearly stopping the recording, that I'll see you on the other side for the continuation of the course.